Okay, let's see how Coyote can be used to find a tricky concurrency bug. Tom Cargill posted a really interesting challenge to the extreme programming community saying concurrent programs are hard to test because of the combinatorial explosion in the state space that must be covered. This is exactly right, and this is exactly why Coyote exists. The state space explodes because of arbitrary context switching in the scheduler, and that's true. So to demonstrate this problem, Tom posted this Java code here. This is an implementation of a bounded buffer or a producer-consumer queue where the put method blocks if the buffer is full and the take method blocks if the buffer is empty. This is using a Java construct called synchronize methods. So to demonstrate this, we're going to try and find the bug that's in this code using Coyote. There's actually an interesting discussion on here that you can see that some people didn't even know that was a bug in here. They kind of challenged, is there really a bug? Because it's hard to find. This is a great challenge for Coyote. Can Coyote find this bug? So to demonstrate this, first we need to port the code to C# because the Coyote engine doesn't work on Java. C# has something different than synchronized methods. We use a C# lock statement on a synchronizing object. So here we do that. Everything else remains the same. We block if the buffer is full, and we pulse or notify when the buffer has changed. Same thing happens in the take method, and everything else remains the same. So now what we want to do is we want to test this using Coyote. Well, first of all, let's just test it in C#. And to do that, we might write a trivial test that creates two tasks. One is going to read, and one is going to write, where the reader is simply just iterating in a loop, calling take. The writer iterates, calling put. All right, so this is setting up two tasks and letting them run in parallel. So this is how we set up some concurrency, and we can test this buffer. All right, let's run that in the debugger and just see what C# does with this, because we run along, we create those tasks, we wait for it to finish, and everything worked, so no deadlocks. So the trivial test then doesn't actually find any problems. So this is a conundrum, and that's why there was an interesting discussion is when you're programming like crazy and doing extreme programming, how do you avoid these kind of bugs when a simple unit test actually fails to actually find the bug, and then something catastrophic happens later on in production? So what we're going to do is we're going to turn this into a Coyote test method. And in order to test this bounded buffer, first we need to do one minor change. And what we'll see is that we've replaced the C# lock statement with a construct from Coyote. And the reason for that is Coyote can't currently intercept the lock statement natively. Instead, Coyote, we have to tell Coyote that there's a lock here, and we do that with this object. The synchronizing block is a thin wrapper on top of system threading monitor, and the wait and the pulse methods remain the same, just operating on the synchronized block instead of a C# lock. All right, so now we've got something that's testable within Coyote, and it's also something that you could ship this in production, because the production version of this synchronized block is a very thin wrapper on top of the monitor class, so it's not going to have any major performance impact in your production code, but it's now testable using Coyote, so that's the key. And we can put this in a Coyote test method. What we first need to do is we need to use Coyote to actually figure out how to reproduce the deadlock. To do that, we've created an interesting test method here that will actually use the Coyote to pick random numbers, and it'll randomize how many reader threads, how many writer threads, how many iterations, and what's the buffer size. So it'll just pick random numbers for all of these things, and now we can use Coyote with a large number of test iterations to find the best test configuration that reproduces a deadlock. So what we can do now is we can test this with Coyote. So let me show you how that works. Over here I've built the samples, and the bounded buffer is in this bin folder right here. So that's what we want to test, and I'm going to test it using the Coyote test engine. Now to install the Coyote test engine, I've actually already built it in the Coyote folder here, which is a Git repo. You could also use the .NET tool that we have instead, but since I've already built it, I've got it right here. and that gives you this command line that allows you to test a program. What am I going to test? I'm going to test the bounded buffer, and I'm going to test, well, first of all, it'll tell me what I can test. These are the different test methods. The test that I want to run is the finder. Of course, if I run the trivial test, it should also confirm, even with 100 iterations of that test, that there's no bug. All right, so that was good there, because that's a lot faster to run 100 iterations than if I did it the other way. All right, so now I want to do this one. I'll ask for 100 iterations. So now it's testing, random number of readers and writers, and it'll do a different number on each iteration. So eventually it'll find, there we go, finally, on just after iteration 20, it found a configuration that actually fails with a deadlock. And you can see that the deadlock was detected, and it found it using 4 reader threads and 5 writer threads, and 6 iterations per thread. So that's 9 threads, and that's a pretty complicated repro, but it still found it. Now Coyote has one more feature which is cool, which is an exploration strategy, where instead of stopping on the first bug, it'll just keep on going. This way we can use this find deadlock configuration test method to find lots of different test configurations, and then we can figure out which test configuration is the minimum test repro. Alright, now I've already done that before, and I've encoded down here the minimum deadlock. Turns out the minimum deadlock is 2 readers, 1 writer, and a certain number of iterations, and the buffer size can be just 1, just to keep it simple. Alright, that's great. That's a minimal deadlock, and already Coyote has given us some benefits here by figuring out what the minimum test repro is, because that helps us understand the bug, and it also helps us have a test code base that is not out of control. One problem with regression testing is you end up with so much code, it becomes a huge anchor on your innovation. Alright, so now we're going to run this, and we're going to run this, let's also run it from C# just to see what happens. And I'll show you the output window here while I debug over here. Step through, wait, oh, and look at that, wait's not returning. So even in the debugger here, we've actually got a deadlock. So great. I can also run that test method right here. Now the interesting thing is, Coyote doesn't hang. So this is cool factor number 2. Not only did Coyote help us find a minimal repro, but when it does run this test, and if you had this in a regression test suite running on your continuous integration test suite, it doesn't hang, and that's really, really important. So instead, it detects the deadlock. Coyote test engine, when it's running, doesn't hang. It actually detects deadlocks. Fantastic. So it tells us there's a deadlock. Now that we've got that, we've got this schedule here that is a repro. Now, so instead of running for a while until it finds a deadlock, we can give it the test schedule like this and use replay. So I'm going to replay the test schedule, and now it's not searching for the bug, it's just got a schedule, which is 1 iteration, and it will reproduce the bug 100% of the time, guaranteed, because that's the guarantee that Coyote makes. When Coyote knows about all of your sources of non-determinism, it can reproduce that bug. So that means I can now reproduce it in the debugger, I can step through, I can watch exactly what's going on, and I can figure out why there's a deadlock. In fact, what I'm able to do now, because of that 100% reproducible guarantee, is that I'm able to instrument both put and take methods with a whole bunch of logging statements, logging the entry, where it waits, where it pulses, where it exits, and I'm able to then store that in a file, run it with 100% repro, and look at the results. And that's how I was able to build this graph. So this graph took all of those instrumented points in both the reader's threads and the writer threads. So we've got 2 readers and 1 writer, as we saw in the minimal repro. And we're able to now chart the timestamps and look exactly what happened to cause this deadlock. All right, so this is great because it's minimum. I'm able to look at it and reason about it. But if I had, if I needed 20 threads, it would be really, really hard to read the graph. So that's why, again, a minimum repro is really important. All right, so to start off, the orange reader thread starts off first, and it finds the buffer's empty, so it blocks on a wait. Same thing with reader 2. And then the blue writer thread kicks in, and it's able to proceed. It fills the buffer, and it sends out a pulse. Now, the really interesting fact here that the diagram shows, which none of us realized was possible, is the pulse wakes up the reader thread, but there's a delay. It doesn't do that immediately. And that delay is big enough to allow the writer thread to re-enter the lock and wait again because the buffer's full. So this is super key to creating a deadlock here. And it's very interesting that the pulse is not instantaneous. It actually can have a delay. All right, so the reader thread then is able to receive that pulse, and reader 1 received it. He woke up. He's now able to proceed and take the item from the buffer and also send out a pulse. And here's key number 2 to creating a deadlock is that pulse wakes up the wrong task. It wakes up the other reader. And of course, that other reader, now that the buffer's empty, can't do anything. He wakes up, sees the buffer's empty, and goes right back to a wait state. All right, but the he woke up the wrong task. If the orange reader woke up the writer, everything would have proceeded just fine. So that's why we need 2 readers and 1 writer in order to reproduce this deadlock. Next thing that happens is the reader 1 goes back to the beginning of that iteration loop and re-enters the lock. There's nothing in the buffer still, so it has to also wait. So now we've got all 3 tasks waiting, and there's your deadlock. To sum up, Coyote was able to help us find a minimum repro in this tricky deadlock bug, so we can actually write a test to explain that deadlock. We're able to then get 100% repro, so we can play with it, we can instrument it, we can look at it and slice it and dice it and figure out exactly what's wrong. And now we've got this beautiful explanation of the bug. We can start to reason about it and figure out a solution. Well, we saw that this pulse woke up the wrong task, so that gives us an immediate hint on how to fix it. And one possible fix is that instead of using pulse to wake up this task, we use pulse all, which will wake up every task. And if we use pulse all every time, then we shouldn't get a deadlock. Let's see what that looks like. So in order to create a test that shows no deadlock with the same configuration, 2 readers and 1 writer, we have a flag on this version of the bounded buffer that switches the bounded buffer from using pulse to using pulse all. And you can see that in the implementation here, where it says, hey, if we're using that fix, let's call pulse all. So now we can actually run this one. So now we can test the no deadlock version in the debugger just to see what happens. It should not deadlock. Now I can run that once here and feel good about it, but what I really want to do now is run that in Coyote as well to be sure. So I can come along here, I can say test bounded buffer no deadlock, and I can say 1,000,000 iterations if I want, right? And it'll run all day long. Or I can say, even worse, I can say different scheduling strategies. So I can say PCT 10 or whatever. We've got a bunch of scheduling strategies, including a portfolio of different strategies and ability to do that in parallel with different test processes. So I'm going to fire up here 5 parallel tasks, 5 parallel processes, each using different scheduling strategies. Each one of those is going to run 100,000 iterations. All right, so this is how I can be sure there really is no deadlock here, and this can run as long as we want, and it should not ever find a deadlock. Alright, so I did that already. In fact, I did 1,000,000 iterations, and so I'm pretty confident there's no deadlock. This is where you get that infinite state space explosion of interleavings between concurrent tasks, and it's super important to be able to test thoroughly if you want that high level of confidence that there's no deadlock. Okay, so I've used Coyote now to also verify the fix.